Okay, hi everybody. So we are at module 4, and in this module we're going to talk about state space approach to control systems. State space approach to control systems. And in particular, we're going to be looking at eigenvalue and eigenvectors. And then we're going to look at the solution to linear time invariant system that is represented by state space representation. So we're going to be looking at eigenvalues / eigenvectors. And then we're going to be looking at the solution to state space equations. Okay, so before we get started, let's do some review quickly. So first thing we're going to look at is the matrix inverse. So if I have a matrix, and let's assume the matrix is square, then we can get the inverse of this matrix, and we denote the inverse as the matrix name and hyphen -1. So that if we have a matrix, then the inverse of a square matrix is denoted by A inverse, and it has the property that if I multiply A by A inverse, this is going to be the same as if I multiply A inverse by A, and if I multiply them together, I'm going to get the identity. So therefore, I'm going to get a matrix that looks something like this: 1, 0, the diagonal elements are 1, and all other elements are 0. The identity matrix. All the way 0, 0, all the way, and the last entry is going to be equal to 1. Now, in order to calculate the inverse of a matrix, we can show that the inverse, A inverse, is equal to the adjoint of A, and this is going to be a matrix divided by the determinant of A, and this is a scalar. So this is scalar, this is a matrix. And this will give me the inverse of the matrix. Now if I look at the determinant, if this determinant is equal to 0, if the determinant of the matrix A is equal to 0, then I'm not going to be able to get an inverse because I'm going to be dividing by 0. Then A inverse does not exist. And in this case, we say A is singular. A is singular. Singular means the inverse of this matrix does not exist. If the determinant of A is not equal to 0, then A is non-singular, and we can find the inverse. Okay, so again, keep in mind, if the matrix is singular, it means the inverse does not exist. If the matrix is singular, it means the determinant is 0, and therefore the inverse does not exist. Okay, now the other thing we're going to look at is the eigenvalue and the eigenvectors. So let's see what this eigenvalue and eigenvectors mean, and then we'll see how they apply to our state space representation. Eigenvalue. Now, some of you might have heard of these, some of you might not have heard of it. So we're going to explain it. and you will be familiar with it. So what is an eigenvalue and eigenvector? If I have a lambda, and this lambda is scalar, and I have v, and v is a non-zero vector, then if I take a multiplied by v, and this happened to equal to lambda multiplied by v, then we call lambda the eigenvalue. We call lambda the eigenvalue of the matrix A, and we call V as the associated eigenvector. What does that mean? So if I have a matrix A, if I multiply it by a vector, and after I multiply this A by the vector, I take that vector, multiply it by a scalar value, and I get the same results in both cases. I call lambda as the eigenvalue, and I call V as the eigenvector. What does that mean? So let's explain what this means in here. So let's do an example to illustrate this. And hopefully this example will make it clear and will give you a visualization of what the eigenvalue and the eigenvector means. So in this example, I have a matrix given A is equal to -3 and 4 and 10 and 15. Now we can think of a matrix like this as a transformation. So what happens if I have a vector in space? Let's say I have a vector, I come here and I plot a vector, and this vector happened to be, for instance, 5 and -1. So this is my vector, this is a 5 and this is a -1. I have a vector here. Now I can think of this A matrix as a transformation. If I apply it to this vector, it's going to transform the size of this vector and the direction of this vector. Make sense? So A given with these values, I can think of it as a transformation that if I were to apply it to a vector, and since it's a dimension of 2, we can visualize it. I can plot this vector here, then apply this matrix by that vector, and see where this vector is going to end up after I do the transformation. So let's see what happens if I take this matrix A and I multiply it by this vector. So what I'm going to do, I'm going to take the matrix -3, 10, 4, and 15, and I'm going to multiply it by my vector. And my vector was equal to 5 and -1. If I do this multiplication, what I'm going to end up with is a vector that is equal to -25, -3 times 5, -15, and -10, -25. And then I'm going to get 4 times 5 is a 20, minus 15, I'm going to get a 5. Together? So this is the result of this matrix transformation. I have a vector that switched from the origin to 5 and -1. Then I did this transformation to this vector, and what happened? I end up with a new vector that is equal to -25 and 5. So therefore, this vector is going to equal to a -25 and 5. This is 5, and this is the vector that resulted from this transformation. And my plotting is not that accurate, but so this is the vector that resulted from this transformation, negative 25 and 5. Now what I notice about this vector is that it is oriented along the stretch of the original vector. So if I were to take a line between negative 25 and 5 and 5 and negative 1, both of them are located along the same line. So if I take a line that stretches like this, I notice that both of these vectors fall along the same line. And I can also show that by realizing I can write this as equal to negative 5 multiplied by the vector 5 and negative 1. You see that? Negative 25 and 5 is the same as 5, negative 1 multiplied by negative 5. So what this transformation did is that it scaled my original vector by a constant that is equal to negative 5. Does that make sense? Okay, so let's continue with this and do another value. So let's say we have another vector and this vector v is equal to 1 and 2. I'm going to do the same thing. I'm going to take this matrix, I'm going to transform this vector, negative 3, 10, 4, and 15. I'm going to multiply it by the 1, 2, and then if I multiply it, I'm going to get a 17 and a 34, which I can write, if I choose, as 17 multiplied by 1 and 2. And again, what do I notice here? I notice here that the original vector was at, let's scale this bigger, the original vector was at 1, 2, so this is my original vector, this is the 1 and the 2, and then after this transformation it became 17, so let's say this is the 17 and 34. If I were to plot this vector, I'm going to see that this vector is located along the same stretch as the original vector. This is 17 and 34. So therefore, we conclude that these eigenvalue and eigenvectors, if I were to consider A as a transformation, then if I have a vector so that when I transform it, that vector after the transformation is still located in the same direction as the original vector, then that vector is considered an eigenvector. And the value by which it stretches or shrinks is the eigenvalue. So again, to conclude all this, we say that the values of 5 and negative 1 and 1 and 2, which are these two vectors, the 5 and negative 1 are this one, and 1 and 2 is this one, this one. Both of these are considered eigenvectors. And the values that we scale the resulting vector after the multiplication is what we define as the eigenvalue. So this 17 and in the previous page this negative 5 are my eigenvalues. So my eigenvalues are equal to negative 5 and 17. Together? Now somebody might think, if I take any vector and I multiply it by this matrix, I'm going to get a vector that is located along the stretch of the original vector. No, that is not the case. So let's look at an example. Let's take another vector. Take a vector that is equal to 1 and 6. And let's do the transformation. So if I were to take -3 and 10, 4 and 15, and multiply it by 1 and 6, what am I going to get? Am I going to get something that is going to be located along the original vector? What I'm going to get is a 57 and a 94. Now you can see that if I do this transformation to this vector, the original vector was at 1 and 6. At 1 and 6. So this is my original vector. Then the transformed vector is going to be at 57 and at 94. So therefore the vector, the result is going to be along this line. So this is my 57 and 94. And therefore you can see that the new vector is not located along the original vector, and therefore 1, 6 is not an eigenvector of the matrix A. Is that clear? I hope this is clear. So this gives you a visualization when we talk about eigenvalue and eigenvector. If I multiply the matrix by this vector, then if this vector is an eigenvector, then the result of this multiplication is going to be the same vector just multiplied by a constant. That constant is the eigenvalue. If I take the matrix multiplied by a vector, and then the new vector is not located along the line that defines the original vector, then that vector is not an eigenvector, nor that value is an eigenvalue. Okay. So let's go back. So this is on the side, so at least you have a good idea of what the eigenvalue and eigenvector is. Some of you might be already familiar with this, some of you might have seen it the first time. Either way, we're going to be using the eigenvalue, and we'll see their significance in a minute. But nevertheless, this example hopefully will give you also a better understanding of what this eigenvalue and eigenvector is. Okay. So if I go back, we said that if I multiply A by the vector V, I should get lambda multiplied by the vector V. And this is what we showed in the previous example. Now I can write this differently. I can write this as the following. I can move this to the other side, and then I can say lambda multiplied by I, the identity matrix, minus A multiplied by V is equal to lambda multiplied by the identity minus A multiplied by V. This must equal to a 0. Because these were equal, I move it to the other side. Then if I subtract lambda V from both sides, this is going to equal to a 0. Now somebody might be not clear as to why multiplied lambda by I, because lambda is scalar. So the way we do it, if lambda is multiplied by a scalar, I can add an identity so that all the diagonals are multiplied by that scalar. Okay, now in this equation, since V is not equal to 0, the matrix lambda I minus A cannot have an inverse. Otherwise, we would have V equal to 0. So since V is not equal to 0, the matrix lambda I minus A cannot have an inverse. Otherwise, we would have something. Otherwise, we would have V. If this had an inverse, I can multiply both sides by an inverse, and then V is going to equal to lambda I minus A inverse multiplied by 0, and is going to equal to a 0. Does that make sense? So in this equation here, I know this might be slightly confusing. This equation here, we said it's equal to a 0. But at the same time, V is not equal to 0. We're assuming V is not equal to 0. Since V is not equal to 0, this lambda I minus A cannot have an inverse, because if it were to have an inverse, I can multiply both sides by lambda I minus A. If I multiply, so I can multiply both sides. Let me multiply them and show you what I mean. If I multiply lambda I minus A by lambda I minus A inverse, so if I take this equation, multiply both sides by lambda I minus A inverse, I'm going to get this multiplication is going to result in a V, and this multiplication is going to result in a 0, which means V is going to equal to a 0, but we already stated V is not equal to a 0. So therefore, we conclude that this means the eigenvalues of the matrix A must satisfy the determinant of lambda multiplied by I minus A equal to a 0. Because if that determinant is equal to 0, it means lambda I minus A does not have an inverse. Does that make sense, the logic of how we followed this? So we started here. Okay, we started here. We started here saying that A multiplied by V, V is the eigenvector, is equal to lambda multiplied by that eigenvector. Now we defined lambda as the eigenvalue. Let me go back here in a second. Okay, here we defined lambda as the eigenvalue, and we defined V as the associated eigenvector. Now what we said is lambda V is equal, A multiplied by V is equal to lambda multiplied by V. Then we said, okay, let's move the right side to the other side. If I move it, this is going to be lambda multiplied by I multiplied by V minus A multiplied by V, and it's going to equal to a 0. But then we said if lambda I minus I has an inverse, I can multiply both sides, and that will result in V equal to 0. And therefore, if lambda I minus A has an inverse, then V must equal to a 0. But we want V not to equal to a 0. The only way that will be possible if lambda I minus A does not have an inverse. So lambda I minus A not having an inverse means the determinant of lambda I minus A must equal to a 0. Okay. So therefore, this equation that we have here is the equation that we're going to be using in order to determine the eigenvalues of any matrix. Now let's see the relationship, before we do an example, let's see the relationship between the eigenvalues and the poles of a system. So before we do an example, let's see what is the relationship between the eigenvalues and the poles of the system. So let's look at the transfer function. So let's consider a single input, single output system that is represented by x dot equal A multiplied by x plus b multiplied by u, and y equal to c multiplied by x. Now we showed before that y of s divided by u of s, if I want to get the transfer function from the state space representation, it is equal to c multiplied by si minus a inverse multiplied by b. Or equivalently, this is the same as saying y of s divided by u of s is equal to the adjoint of si minus a divided by the determinant of si minus a, because I have a b here and I have a c here. This is how I calculate the inverse of the matrix. The adjoint of si minus a, of course s here is small letter, even though I'm writing it bigger than it should. This is a small letter, the s that we know, the Laplace s. Okay, so therefore, if I look at this transfer function, this is a transfer function. What are the poles of this transfer function? The poles of this transfer functions are the values of which, of s, for which this determinant is equal to 0. So if I take the roots of this determinant, that will give me the poles of the transfer function. So coming here, because everything else is going to be in the numerator, the only thing I have in the denominator is this determinant of si minus a. And therefore, if I want y of s over u of s, this is equal to the transfer function. If I want the poles of the transfer function, I'm going to have to take the roots of the denominator, which is the determinant of si minus a. So therefore, this is an important conclusion, which says that the poles of y of s divided by u of s are the values of s for which the determinant of si minus a is equal to a 0. I'm going to highlight that and put it in a box. Now, if we substitute lambda for s, it is clear that the poles of y of s divided by u of s are nothing different than, can you guess it? Than the values of lambda. If I look at this equation here that I use for calculating the eigenvalues, and I look at the equation here that I'm using to calculate the poles, they are the same, except for I have to replace s with lambda. So we conclude, if we substitute lambda for s, it is clear that the poles of y of s divided by u of s are equivalent to the eigenvalues of a. So that is another insight. When I have a matrix A that I got from a transfer function, when I calculate the eigenvalues of A, that is the same as if I were to calculate the poles that we're familiar with from linear control of the transfer function. And this is the significance of the eigenvalues. Okay, so let's do an example. And let's start a new page. So continuing with the example that we started with, the mass damper example. So we have a transfer function if you recall was equal to y of s divided by u of s equal to 1 over m multiplied by s plus b divided by m. Now if I look at this transfer function, the poles of this transfer function, poles are at s equal to 0 and s equal to negative b over m. Make sense? The roots are at, and what am I missing? I'm missing an s here. When s is equal to 0, this is the root, and when s is equal to negative b over m, that is another root. Okay, so this is the first representation, or one representation. Now if I look at the state space representation, that we calculated earlier, the state space representation x dot equal to a multiplied by x plus b multiplied by u and y equal to c multiplied by x. In this case, a is equal or was equal to 0, 0, 1, negative b over m. This is the state space representation. Now what I'm going to do, I'm going to calculate the determinant. I'm going to calculate the eigenvalues of this matrix A. So what I want to calculate, I'm going to calculate the determinant of lambda multiplied by I minus A. What is lambda multiplied by A minus A means? It means the determinant of lambda 0, 0, lambda. Does this make sense? Not sure if this might be confusing to some, but I'm multiplying the identity. Since this is a 2 by 2 matrix, the identity is 1, 0, 0, 1. And then multiplied by lambda, I'm going to get lambda 0, 0, lambda, which is what I got here. Minus A, and the A matrix was a 0, a 0, 1, a 0 of negative b over m. And I want to calculate the determinant of this. What is this gonna? I can simplify this. Lambda minus 0 is going to be a lambda. 0 minus 1 is going to be negative 1. 0 minus 0 is a 0. Lambda minus b over m is going to be equal to lambda plus b over m. So I want to calculate the determinant for this matrix. Now what is this determinant equal to? So let's put this in a box. Oh, I'm going to be using these boxes. This looks nice. The determinant of a 2 by 2 matrix, and the matrix, if the matrix is equal to F11, F12, F21, F22, is given by F11. I should probably have made this smaller letter. F11, F12, because these are scalars, just 21, F22. The determinant of F is going to equal to F11 multiplied by F22 minus F21 multiplied by F22. So I multiply this by this, and I subtract from that this multiplied by this. Okay, so therefore, going back to our example, if I want to calculate the eigenvalues of A, the eigenvalues of A, I'm going to use this fact that we just stated here, and I'm going to calculate the determinant of lambda I minus a, which is going to equal, I'm going to multiply lambda by lambda plus b over m minus -1 multiplied by a 0. So again, I'm going to be multiplying this with this, and I'm going to subtract this multiplied by this. So if I do that, I'm going to get lambda multiplied by lambda plus b over m, and this is equal to a 0. This means I have lambda equal to a 0 and lambda equal to -b over m. And if I look at these values that I got for the eigenvalues, these eigenvalues are the same as the poles of the system. And these are the same as the poles that we got from the transfer function. So we conclude from all this is that if I have a system that is represented by the state space representation, then the eigenvalues of the system matrix is equivalent, are the same as the poles of the transfer function. Okay. Now, since these eigenvalues are the same as the poles, I know how to determine whether the system is stable or not. A system is going to be stable. We know from previous knowledge that if the system is stable, if each pole has a negative real part, and therefore the poles have to be in the left half plane for the system to be stable. Now, if the poles are the same as the eigenvalue, then we conclude that for the system to be stable, each eigenvalue of the system matrix has to have a negative real part. So a system is stable if I'm dealing with poles. Each pole has a negative real part. And if I'm dealing with a state space representation, the system is stable if each eigenvalue has each eigenvalue of the system matrix has a negative real part. Okay. So again, to recap what we've done, so we introduced the concept of the eigenvalue, eigenvectors. We explained what the eigenvalue, eigenvectors mean from the algebraic point of view or from a transformation point of view. We said the eigenvector is a vector, so that if I multiply the matrix by that vector to transform it, the new vector is going to be aligned along the same direction as the original vector. If that is the case, then that vector is considered an eigenvector, and the scaling by which that vector is going to go through after I multiply it by that transformation by the matrix is going to be my eigenvalue. Now then, we said, okay, now we are interested in what these eigenvalues mean, and when we did some development to show that the eigenvalues of a matrix satisfy the determinant of lambda I minus a equal to 0, we realize that this formula is similar to that we use to calculate the poles of the system, and therefore we concluded that the poles of the system are nothing other than the eigenvalues of the system. And therefore, if I have a state space representation, if I use the system matrix A, I can calculate the eigenvalue for that matrix, and that will be the same as the poles of that system if I were to express it in transfer function. Now, for the system to be stable, we know that all the poles have to be in the left half plane, and that is equivalent to saying all the eigenvalues have to have a real negative part. Okay, I'm going to stop here, and I'm going to do the solution of the linear time invariant systems in the next module. Thank you, everybody.